Okay, in this section, we're going to do a little bit more practice problems, and we're going to introduce a new concept. The concept you've already been exposed to. I just haven't given it a name. You were exposed to it earlier in this unit, but I'm going to bring it up again. So again, just remember 1 mole means this many things, and I know I sound like a broken record here, but for those of you who are unfamiliar with this, or if you're intimidated by this number, the more I say it, the more you'll get used to it. So here's the first question. I have 1 mole of oxygen atoms. How many oxygen atoms do I have? You can pause here, think about it. This one again is relatively straightforward. 1 mole is just another way of saying this many things. So if I have 1 mole of oxygen atoms, I have 6.02 times 10 to the 23 oxygen atoms. Next question is a little different. I have 1 oxygen atom and I have 1 hydrogen atom. Which one weighs more and why? And you can pause and think about this. This is actually related to something that we discussed earlier in this unit. Earlier in the unit, I showed you a slide, and I showed you a typical oxygen atom, which is shown here on the left, and I showed you a typical hydrogen atom, shown here on the right. And at the time, we said, look, the oxygen atom weighs about 16 times more than the hydrogen atom. So that basically answers this question. I have 1 oxygen atom and 1 hydrogen atom. Which one weighs more? It's the oxygen. The oxygen weighs about 16 times more. More formally speaking, its mass is about 16 times larger than that of the hydrogen atom. Next question. I have a dozen oxygen atoms and I have a dozen hydrogen atoms. Which weighs more, the dozen oxygens or the dozen hydrogens? Again, you can pause and think about this. This one should be relatively straightforward as well, because each of the oxygens weighs 16 times more than each of the hydrogens. So if I have 12 oxygens and 12 hydrogens, the 12 oxygens are going to weigh about 16 times more. And again, this should be a review, but sometimes it takes some getting used to. I have 1 mole of oxygen atoms, and I have 1 mole of hydrogen atoms. Which one weighs more and why? You can pause here. And the answer is the same. The 1 mole of oxygen atoms, in other words, 6.02 times 10 to the 23 oxygen atoms, weighs more than 6.02 times 10 to the 23 hydrogen atoms. And we talked about this earlier in the unit, but just to emphasize it again, 1 mole of hydrogen atoms weighs this many grams. And all you have to do is look over at the oxygen box, and you can see that 1 mole of oxygen weighs about 16 grams. Here I'm rounding up, don't worry about the 0.999. This is basically very close to 16. And this is because each oxygen atom is about 16 times heavier than each hydrogen atom. So you can look at any of the elements in the periodic table and figure out how much 1 mole of those atoms weighs. 1 mole of nitrogen weighs about 14 grams. 1 mole of chlorine weighs about 35.5 grams, roughly. 1 mole of sodium weighs about 23 grams. So this is the new concept that I want to bring up and give a name for. If I asked you what's the mass of 1 mole of hydrogen atoms, all you have to do, and all I expect you to do, is to look at the periodic table, look at this number, and say 1 mole of hydrogen atoms has a mass of about 1 gram. If you want to be precise about it, you can say it has a mass of about 1.0079 grams. This concept, how much 1 mole of something weighs, is called molar mass. So as the course goes on, molar mass is going to come up again and again and again. So it's worth committing this to memory. Molar mass is just a way of saying how much 1 mole of something weighs. So the molar mass of hydrogen is about 1 gram. The molar mass of beryllium is about 9 grams. The molar mass of neon is about 20.18 grams. And you can do this for any of the elements. And we can do something else with molar mass, which we'll do in a few slides. But I want you to know what molar mass means. Molar mass is how much 1 mole of something weighs. So again, I can ask you, what's the mass of 1 mole of beryllium atoms? This is just another way of saying, what's the molar mass of beryllium? Because I'm asking how much 1 mole of beryllium weighs. The molar mass of beryllium is about 9 grams. If you want to be very precise, 9.0122 grams. Next question. What's the mass of 2 moles of oxygen? So now I've changed the number of moles. But you can do this one relatively easy. If you want to pause and think about this, you can do that now. The way to do this is you say, look, 1 mole of oxygen weighs about 16 grams. Again, I'm rounding up. So if 1 mole weighs 16 grams, 2 moles must weigh twice as much. So 2 moles of oxygen atoms weighs about 32 grams. Next question. What's the mass of 1.5 moles of carbon atoms? Again, you can pause here and think about it and work it out. The way to do it is to look at the box for carbon and you say, well, the molar mass of carbon is about 12 grams. What that means is 1 mole of carbon weighs 12 grams. How much does 1.5 moles of carbon weigh? It weighs 1.5 times this, which is about 18 grams. So the answer to this question is that 1.5 moles of carbon atoms weigh about 18 grams. And again, this is, you can relate this all back to the idea of molar mass, which is how much 1 mole of something weighs. So I want to summarize the mole a little bit now, just to sort of recap and have you think about it again. Mole is just an easier way of saying this number. Second point, and this is important, which is why I've made the text bigger and italicized it and put an exclamation point here. 1 mole of an atom also equals the atomic mass number of that atom in grams. This is just me rephrasing what I showed you back here. 1 mole of hydrogen weighs about 1 gram. 1 mole of boron weighs about 10.8 grams. So this is relatively important, and it's going to come up in the course over and over again. And then another thing to know is that this number, 6.02 times 10 to the 23, is sometimes called Avogadro's number, so if you hear me say that, that's what I mean. Sometimes it's called Avogadro's constant as well, same thing. Another thing that I want to emphasize, just in case you're a little bit lost, is how these, the things that we've been talking about are related to each other. And what I mean by that is, if I tell you how many atoms I have of something, then you can use this information to figure out how many moles of that something you have. And if you know how many moles of that something you have, you can use the periodic table to figure out how many grams of that something you have. And I'll show you a couple of concrete examples now. But the idea is that this information can go in either direction. If I know how many atoms of something I have, I can figure out how many moles of it I have. If I know how many moles of something I have, I can figure out how many atoms I have. And if I know how many grams of something I have, I can figure out how many moles of it I have. And I'll show you how to do that in a little bit. But a concrete example, imagine that I have 6.02 times 10 to the 23 carbon atoms. I can use this information to figure out that I have 1 mole of carbon atoms in this case. And if I have 1 mole of carbon atoms, I can use the periodic table to figure out that 1 mole of carbon atoms weighs about 12 grams. And you can do this in reverse. If I told you you had 12 grams of carbon, you could use this information with the periodic table to figure out that you had 1 mole of carbon atoms. And if you had 1 mole of carbon atoms, you could figure out that that is equal to 6.02 times 10 to the 23 carbon atoms. So the information can flow in either direction. And again, I won't spend too much time on this, but you can do the same thing for any of the 118 different elements. If you have 6.02 times 10 to the 23 hydrogen atoms, that means you have 1 mole of hydrogen atoms. And if you have 1 mole of hydrogen atoms, you can look it up on the periodic table and figure out that that's equal to about 1 gram of hydrogen. So I want to emphasize this relationship in a slightly different way, and I want to focus on these last 2 related ideas, how many moles you have and how many grams you have of something. And this concept is important enough that it deserves its own slide, and you will hear me say this a fair amount throughout the rest of the course. If you know the number of moles of something that you have, and you know the chemical formula of that something, you can figure out how much it weighs. You can figure out how many grams of it you have. And this works the other way too. If you know how many grams you have of some substance, and you know the chemical formula of that substance, you can figure out how many moles you have of that substance. And we're going to do a few examples on the next few slides, and they will get progressively more complicated. So here's a mini periodic table. Obviously not all of the elements are here, but enough that we can answer the questions that I'm going to show you. So, first question. I have 8 grams of helium atoms. How many moles of helium do I have? You can pause and think about this. The answer to that question is basically obtained by looking at the helium box and knowing that this number is the molar mass of helium, which means 1 mole of helium weighs about 4 grams. But I told you that you had 8 grams of helium. So if you have 8 grams of helium, 8 grams is twice as much as 4 grams, right? So if 4 grams is 1 mole, 8 grams of helium atoms has to be 2 moles of helium. So that's the answer to that one. Next question. I have 8 grams of helium atoms. How many atoms of helium do I have? And again, on the previous question, I'm going to pause for a second and let you think about this. So, if you've unpaused, on the previous question, we said that 8 grams of helium is 2 moles of helium. Well, we know that 1 mole of helium atoms is 6.02 times 10 to the 23 helium atoms. 8 grams of helium atoms is twice that much. So the answer to this question is 2 times 6.02 times 10 to the 23 helium atoms. In other words, if you have 8 grams of helium atoms, you have 2 times 6.02 times 10 to the 23 helium atoms. And so that is a relatively complicated problem, but you can figure it out in 2 steps. The first step is you say, I have 8 grams of helium. How many moles of helium do I have? Well, I have 2 moles of helium. If I have 2 moles of helium, how many atoms is it? Well, it's 2 times Avogadro's number, or 2 times 6.02 times 10 to the 23. Next question. I have 21 grams of nitrogen atoms. How many moles do I have? And again, the way to do this is as follows. Actually, I should let you pause and try to work it out. So I'm going to clear away a lot of the elements here and just focus on nitrogen, because that's what this question deals with. So I have 21 grams of nitrogen atoms. How many moles do I have? Again, you focus on the box for nitrogen and you focus on this number, which can be used for the molar mass for nitrogen. And again, molar mass means how much 1 mole of nitrogen atoms weighs. So 1 mole of nitrogen atoms weighs about 14 grams. So I'm going to write that as a fraction. Focus on the left-hand side here of the equation. 14 grams of nitrogen atoms is the same thing as 1 mole of nitrogen. This is just a more detailed way of writing the molar mass. And then you say, but I don't have 14 grams of nitrogen. The problem says that I have 21 grams of nitrogen atoms, so I set up an equivalent fraction off to the right, 21 grams of nitrogen atoms in the numerator, and I don't know how many moles of nitrogen atoms that is, which is what the question is. So we call that x. We want to figure out what x is, so we cross multiply. That turns out to be 14 times x over here is equal to 1 times 21, which is over here. We want to get x all by itself, so we need to get rid of this guy. So we divide both sides by 14 grams of nitrogen atoms, and x moles of nitrogen atoms equals 1 times 21, which is just 21, divided by 14. So the answer, or what x is, turns out to be 21 divided by 14, which is 1.5. So if we have 21 grams of nitrogen atoms, we have 1.5 moles of nitrogen atoms. And that's basically how you use molar mass to figure out how many moles of something